Okay, so in part one in the previous video, we looked at implementing the fan in pattern in Go using generics. This is a pattern that I have to re-implement all of the time, and once and for all, I wanted to nail it in generics. Today, we're going to continue on this theme and look at fan outs, which is the sister pattern to fan in, the complete opposite in terms of what we're trying to achieve. So if you haven't seen part one, maybe go and watch that first. If not, let's dive into what we mean by fan out. So first things first, yesterday we looked at this fan in. The principle behind fan in is multiple producers. They can be any source producing data that then come in that we want to consolidate into a single consumer that the whatever's going on here can consume as if it's coming from one place without needing to worry about whether or not it's actually come from multiple sources. Fan out is the complete opposite kind of problem. You have a single source. I've written a DB, but it doesn't need to be. It could be a queue, it could be a worker, it could be whatever you want. That is producing data that you then want to fan out right out into multiple consumers. Each thing here doing something different with the same data. This is what we want to implement today. Examples of this, let's think about log streams where you want to send off your logs to an analytics platform as well as your internal consumer event platform, for example. Hundreds of examples I can think of just in the past few months that I've had to implement fan out. And we're going to look at how to do that in generics right now. So first thing we'll do is let's think about the API that we want to implement here for fan out. And we'll do that just as you always should, which is by thinking test first. So let's write our test function. Okay, so let's imagine we have some data source. Let's say it's a source, and it'll be a channel for the point of view of fan out. Because we want to be generic, channel is a good way to provide a stream of data. And the source chan, let's make them. Yesterday we had a channel of strings. For the last video, let's try a channel of integers instead. We don't really need a buffer. Also, in terms of what's actually going to go into this channel, let's just create a slice of integers, and we will give it a size of 10, capacity of 10, and we can just range over this and get the data that we expect into the channel. Okay, cool. So that's kind of just a little bit of setup. We're going to write integers into the channel. Let's think about this API. Probably we're going to want to call a new library method that gives us a new fan out instance. In this case, it'll be generic and it will take in an integer type. And yeah, this is going to then run the process of doing the fan out for us. And this is what our library will provide us. Next, we want to think about our outputs. So if we think about those as destinations, we want two destinations for the point, let's say, of testing. We'll just try two. Yesterday, when we were looking at this, we used this term register, and we registered a source. So let's today have the same principle. We're going to register a destination. Yesterday we provided here, we've defined it as 0, but this buffer to the channel that we get back here, and I quite like that, that we can provide this buffer so that in theory you could create yourself a buffer channel if that was going to be useful. And then, yeah, great. Okay, so these are our two destinations. What we'll then probably want to do is actually kick off the process. Okay, so we have our input, we have our output. Yesterday we ran this method fan out start. I'm assuming, because this is going to run the fan out process, we'll want to pass our source channel in here so that it knows fan out this data. Now we want our input channel needs to be written to, right? So let's do that in the background. So we have this input slice. We'll get range input data. There's really no need for us to have declared this slice up here, but it's nice just to say here's our data and here's the channel. If we range over it, what we're going to do is for each value, we'll write it to our channel. So this is our producer, yeah? The producer will write the data onto the channel, just as if you imagine a database or a queue or your worker would output this data, exactly the same principle here with our slice. And then for the principle of the test, what we'll also want to do then is read our outputs. So if we range over the values in destination 1, we're going to want to output these somewhere. So let's say results 1, and we'll just results 1, we'll append results 1. We'll just, whatever comes off the channel will go into there, and we can then assert against it. Of course, you could do this programmatically, so I've created these explicitly, but you could just loop over. Let's say you have a dynamic number of destinations, as you may well do. You could just loop over them for each one, register them, and write to them. Okay, cool. Oh yeah, and we just need to do the same here for results 2, because we're fanning out to 2 places. So we need that to be 2, and we need to read the channel. So yeah, all we're doing here for each destination channel that gets written to here, so destination channel 1, destination 2, you could have as many as you wanted. But for each destination channel, we expect data to come onto it. We'll push it into this slice so that we can then assert it for the purpose of the test. In reality, you're just going to want to consume this channel and do work. Perhaps you want to make a request somewhere, perhaps you want to do something else to process it. I don't know. But for the point of the test, we're just going to push it back to a slice. And then right at the end, we're just going to test that results 1 and results 2. Now, what do we expect of them? Well, because it's a fan out, what we're expecting is whatever comes out here goes on to here. Now, what comes out of the input in reality is whatever's in this, whatever comes out of this input data slice here, which is just the values 1 to 9. So if we create an expected, this would be 1, 2, 3, 4, 5. Sure, there was a quicker way to do this than doing this game manually, but it's nice to see it and verify it. And then for each, we're just going to assert that expected gets that. Okay, so that's the basic API. So before we actually try and run this test, we know it's going to fail. Let's have a think about implementing the actual library to deliver fan out. So the first thing we need to do is create a new file where we'll actually implement fan out, and we're expecting to be able to call new fan out and get back some kind of type. So if I call fan out, and it'll be a structure, we're not exactly sure what's going to go in here. We do know that we're going to need it to be generic, and it's going to have a type that is going to fan out, which in our case will be an integer. Then we need to define a new function with the same type argument, which will return a pointer to this fan out instance. Cool. Okay. So that satisfies the basic setup method. We need to register a destination. What that means is we need to register, hey, we've got another place to send this data to. Give me a channel where you will write that to. So let's go call that, so what would we call it? Register destination. It took this buffer argument, remember, so I'll add that in. And then what we're returning here is a channel. And if you remember from the previous video, we want this to be a read-only channel, which is what this syntax means. We will be the ones closing the destination channels internally, so we need that to be read-only. So what we need to do is make this channel, it will be of type T, and we're going to support this buffer value. Then we want to return the channel, but we also want to store that channel so we know where to write it to. So let's have a new field, destinations, where we will push this channel to, and this can go, no, we don't just set it there, but we do need to set here destinations, which will be a slice of channels of type T. And then we've stored those so that we can then write to them later. Now, finally, we've got this start method that we need to implement. So let's think about what start method will be. There we go, start. Okay, so, yeah, first thing is we need our source channel, which would be the channel of type T. Now, remember that will also be read-only. We won't be able to close that. And yeah, okay, so this is actually where fan out is going to happen, okay? So let's have a think. First thing we need to do is range over that source chan. So the value that we get off a source chan, then for each destination, so if we range over destinations, for each destination we want to we want to write this value, and also, by the way, this is a write only channel from our point of view. We don't want to be reading this ever, which is why I've done this. Okay, cool. So why are we getting errors here? Yeah, I haven't put in the range. That's one of my common mistakes. Cool. Okay. So we've implemented this. It should build. There are no errors. So let's have a think. What happens if we run it? Well, it hangs. And it hangs for a few reasons, I think, at least. Yeah, so the very first thing is this start. What this is going to do is this is called ranging over the source channel. And this will only stop when the source channel is closed. But the source channel is only being written to after start. So the very first thing that we need to do is make this non-blocking. Now, we could actually just put go hit, and that would make it non-blocking. But given that this is always going to be an issue, my preference actually would be that we make this a feature of the library that start is never blocking. And therefore, we never have that issue when using the when using this package. So what that will mean is that start no longer blocks. What it should then go on to consume this data, should then write to the source channel, read from the destination channel, and then we can assert at the end. So what happens now? Well, we get a failure, which doesn't surprise me. Well, yeah, first things first, we do need a 0 in here. Yeah, next thing is this we only got a partial data here, so we only ended up getting 4 numbers when we were expecting 10. And let's have a look at why that might be. We're running these in we're reading from the destination channels in Go routines. The reason that we're doing that is that in real life you would want these processes to be in parallel. You would want them to be independent of each other, running in parallel, doing the work. That's the whole point of fan out. So we've run these to test that theory in Go routines. However, because these are non-blocking, we're then asserting on data they are writing before they have necessarily finished, because these may finish at any point. So what we need to do before we assert is make sure that actually we know that this work is done. Now, in real life, you wouldn't necessarily need to do this because you wouldn't be waiting for any result. This is more like to be an ongoing process, that something produces data and then something else happens. But in this case, we want to know when this is completed so that we can assert on outputs for the purposes of test. So what we can do is use a wait group. We know that we're doing just 2 tasks here. Inside each non-blocking task, we will call done when they're done. And then if we wait on these, what should happen in theory is we will only assert on the value of these slices, results 1 and results 2, once the processes that write them have completed as assured by done. So let's try that again. Okay, and we're back to a blocking situation because there's one other thing that we haven't thought about here. So let's have a think about what that is. We are blocking here until both of these ranges, these loops, have completed and called done. Now, when does looping or ranging over a channel finish? It finishes when the channel being looped is closed. And as you'll remember, we haven't closed those yet. So what we need to do is, once all of the work is done, which is happened here, once all of the work is done, we need to then go back over the destination channels and close them. So I'll call close on this one. So what we're basically doing here is we're saying once the input is completed, so once the source is completed, this range will complete. Once we've written, these ranges will complete, and then we can close the destination channels. So let's run that and see what happens. And we're still blocking. So let's take that reasoning one step further. What we know is we're waiting on this, and this is waiting on these dones. Those done calls only happen when these channels are closed. We're closing each of those channels here, but that will only happen once the source channel is complete, because we're also ranging over that channel. So where is the source channel being written? It's being written here, yet we are not closing it. So what we need to do is also close the source channel. So to play that forward, by closing the source channel once we've written to it, this for loop can finish once it's been processed, and then close the destination channels. Downstream, the destination channel loops will complete once those destination channels are closed. The dones are called on the wait group. The wait is satisfied, and then we can assert. And if we run the test, just like that, magically it works. So that is fan out. There's one other thing we might want to think about here, which is that we're writing to these destinations, and in real life, these destinations will have very different characteristics. One might be a very quick queue, a fire and forget queue. One might be a slow, synchronous piece of work that needs to go and happen. What we're doing when we're writing here, looping over each destination channel, we're blocking on writing to the next channel until after this channel has been written to. That means that we're actually synchronizing production across the fans, and that creates a problem because it means that the slowest fan can only go as fast, the fastest fan can only move as fast as the slowest fan. You could get around this a little bit with buffers, adding buffers to the destination channels by passing those in here. Ideally, however, you'd want each of those writes to be independent. One way to do that would be to run these each in a go routine so that it doesn't block. However, that introduces a new complexity because we're closing all of these channels here. And if we close these channels without knowing that all of the writes have completed to the channels, we're creating the potential for a panic. So that's actually a bit of complexity that we're not going to deal with today, but something that you would want to address. You would want to make sure that we can close each of these channels after all the writing is done, but that the writing is not synchronized between destinations which have very different performance characteristics. So I'll leave that as a kind of open question, and maybe in a follow-up video we can have a think about how we would solve that problem. What I'm going to do now is I'll push this as is to the library where I maintain this. So you can see the link here at the bottom of the screen, but I'll also put that in the description. Thank you very much for watching while we've implemented fan out today. Do go back and watch fan in part 1 if you haven't seen that. And if you have any questions, let me know in the comments. Thank you very much for watching.